Yes, ma'am.
Okay, just a second. Recording is on. Just a second. Okay, so we'll just start. So I think there were few who were not. I'm audible, right?
Yes, ma'am.
Yeah. So previous class, we started off with KNN algorithm, but I think there were few who were not there. So we'll just quickly browse through. Okay, these were just classification examples. So hope you remember the difference between classification, regression, supervised, unsupervised, and all that. Okay, so those basic things, I think I have put the slide for the first lecture also. So people would have gone through if they got time, or else you can go through when you are free. So now you are aware of what is classification, clustering, and all. See, I know that there are few who have already done projects, or you are familiar with, or maybe you have done electives which are related to machine learning. So sometimes it might look that it is very obvious things what I am talking about, but then there may be few who have not done, because you didn't have a course as such, generic, I mean, a core course where you learned machine learning. So sometimes I'll have to think that there are some who don't know what is machine learning. So it might be that way. If everybody knows that, you can ask me, we'll just make it fast. So then we have supervised, unsupervised, etc. Okay. Now what about k nearest classifier? K nearest neighbor classifier. So we talked about how to find the neighbors. So what we are doing in KNN classifier, we'll take, so we can think of, like, say, we'll ask the first, say if I say k equal to 5, I'll ask my 5 nearest neighbors of the entire data. And for these 5 nearest neighbors, majority are telling one, having one class. I tell the new instance for which we are trying to predict, that also we will be classifying it to that majority class. So for example, I have to predict whether the disease is present or not, okay, or the mail is spam or not. So now say for example, I am telling k equal to 5. Now in that case, I will find my 5 nearest neighbors. So how do I find 5 nearest neighbors? Based on the distance. So usually Euclidean distance. Okay. So we have other other measures also, but the very basic distance measure would be your Euclidean distance. So now you find the Euclidean distance of the new instance for which we don't know the class label. Okay, so that is like a query instance. Okay, so for that we find the distance between this query instance or unknown instance and all other instance in your instance means each record. Okay, so unknown instance, sorry, all other instance in your data set. Now so you are finding the distance. Now you find the minimum 5 distance, because now we told that in this example k equal to 5. So we find the 5 minimum distance in that. So you get whichever samples had that will be your 5 nearest neighbor of the unknown sample, or your what is that query sample. So now we get 5 nearest neighbors. In that neighbors, we see whether the mail is the label for the mail is spam or ham. Now if majority, like say for example, we have 3 as spam and 2 as ham, we classify the unknown sample or your query sample also as spam, whichever is the majority. Okay, there was a confusion I actually could not go through because of I was not well. I'll go through and let you know about, there was a query asked in the previous class. Anyway, I'll clarify and then discuss here. So usually we try to choose k as odd numbers to avoid a tie. Okay, so k will be usually when we take KNN classifier, preferably we take k as 1, 3, 5, 7 odd numbers. Okay, so that much I think we have discussed. Okay, so and also there was one more thing we mentioned about a lazy learner and an eager learner. So now usually when we talk about other classifiers, like you would have heard the names like say naive Bayes, SVM, or other algorithms like decision tree and all that. What happens is, say you have 1,000 data in the training set. So as and when you get the data, like if you give it to the model, I mean, it actually generates a model from and creates a learning from this 1,000 data, and it is ready to predict a new sample. That's how it is. So when you get the training samples itself, the model is generated and it tries to establish some kind of relationship to, and it is ready to predict the output when a new unknown sample, I mean, a new sample with unknown label is given to it. That is eager learner. Okay, but till it will not wait till a test tuple or a prediction to be done. It will always be ready as and when it gets the training data. Whereas in your lazy learner, if you have noticed, in this case, say KNN does not do anything initially. Only when you ask the model to predict a label, that's when it starts doing some distance measure, find nearest neighbor, etc. So till then it does not do anything. Okay, it simply shows it. So it is called lazy learner. Like we have the terminology itself is like that. So only when there is something to predict, it starts learning something. Okay, so that is our so our KNN is a lazy learner. Okay, so I think we saw an example also, like say we have two parameters. So this is like a two-dimension data. We have two parameters or attributes, and there is a class. Now in this, the new instance is mentioned in the last line. X1 equal to 3 and X2 equal to 7 is the new sample for which our label is not known. We don't know whether the classification is good or bad. Okay, so then we find that new sample, we find the distance with all these four samples, and we take k equal to 3 in this example. So we find three distance and then we sort the distance and we take the smallest 3 distance. Okay, so then what happens? You get the 3 nearest neighbors. Now that was this. Okay, so it is Euclidean distance, and they are just finding squared distance because we are anyway going to just compare. So squared distance is also fine. So now we are ranking the minimum distance. So it is like say third instance, fourth instance, and the first instance. So these are all the instance which you will take as 3 nearest neighbors. Okay, so the second instance we are not taking. That's what is that last column telling. Okay, now sorry. So now if we look, we have 3 nearest neighbors and 2 of them are good, and 2 of them has the label as good and 1 is having bad. So our prediction would be for the new instance would be as good. Okay, so this is the simplest form how your KNN would work. Okay, so hope it is clear. Even if you have missed previous class, I think we have roughly now discussed. So I don't think there is a big deal. It's not like you have a lot of calculations and all. It's like very basic calculation of your distance. Okay, so here we have taken that, how we have taken SK. Now, how do you choose K? Okay, so if K is too small, then it would be like if you have noisy points, now our prediction would be affected with that, because we have only 1 or 2 neighbors. Based on that, we are going to predict. So maybe if there is noisy data, because we have considered only 1 or 2 or 3 points, maybe one of them can be noisy, and then still our prediction is made depending on that, and then it goes wrong. So that can be possible. If K is too large, what happens? You might, like if you make, say we have only 15 instance and then we make K equal to 12, then you might have like points which are belonging to the other class. We even consider them and we create a confusion. So actually K needs to be identified properly. So how do we usually identify a good value of K? So it's usually by, like say for example, we'll start with a K equal to 1. We identify with some test samples the error made by the model, and like this we keep on increasing our K by 1, like K equal to 2, K equal to 3, K equal to 4, and so on. And from where you get a good accuracy or a less error, there we stop. Okay, so that's how we choose usually, because we cannot suddenly say K equal to 6 is apt for this particular model, etc. Okay, unless there is some previous study. Okay, so that's how we vary the K and see whether it is the model is performing well. Whichever is the K where we have less error, that's the model that's the K we choose or fix. Okay, now what if the attributes are non-numeric, like we can have say color. Okay, So color may not have a value like 1, 2, 3, 4, isn't it? It may be blue, it may be black, and it is discrete values. It's not like numeric, some we have some continuous values or some values. It's not a numeric value. It is having some categoric values. So like say blue, black, red, etc. Now how do we find the distance? We can't find the distance between blue and black, no? So we don't know. So now what we can do is, one approach is, say for example, that particular attribute, when you're comparing two instances, say x1 and x2, okay, and then we see the color, okay. How do we find the distance? If the previous example, if you remember, the first x1 minus x2, same way, like if you see the previous example, see here 7 minus 7, or if the new data is, what is our new data actually, 3 comma 7. So when I say 3 comma 7, what happens? How do we find the distance between this and the first instance? 3 minus 2, sorry, 3 minus 7 the whole square plus 7 minus 7 the whole square, isn't it? So attribute wise, x1 corresponding x1s will be found the difference and then the square and add it. So when you have a color attribute, so what do we do? So what happens is, the two instances what you're going to compare, their particular color attribute we see. If they are both same, like say query instance also color is blue, the instance one also color is blue, we can say the difference is 0. Okay. If query instance color is red and then we have the first instance color as blue, then they are different. So we just directly give 1. That is one approach. Okay. Because there is a difference. So we are just telling there is a difference or not. So that is how we are calculating. So it will be 0. That difference would be either 0 or 1. Okay. So that is one approach. Or there are other very complex approach where you give large scores for very different colors, and then very similar colors we might give, like say pink and say maroon, something like that. So they get a very small difference because they are very similar, isn't it? So you can even do that. You can give certain colors, certain numbers, so that it gives a particular difference which will be very meaningful. That is also possible if that color has a lot of contribution and all. We may have that kind of a sophisticated approach also. But otherwise, we just very simple method would be, we'll just see whether they are same, the categoric attribute which we are considering. If they are same in both the instances, what we find the distance, we'll just say it is 0. If they are different, we'll just put 1. Okay, is that clear? Any confusion in this? Okay. So that's how we'll handle our, KNN would handle our numeric attribute. Okay, non-numeric attribute. Now, how to determine a good value of k? This is what we discussed. Starting with k equal to 1. Okay, we use a test set to estimate. So we have certain test set where we know the label also. We try the model to predict, and then we see whether error is high. So like this, we repeat by adding k each time one by one, and then we see whether our error is increasing or decreasing. When we have a minimum error rate, we stop our k. So that is our k. Okay. So that's all about how do you determine a good value of k. Now there is an advantage of KNN. So what are they saying? When new labeled instances become available, we don't have any complexity in our model, because the model will not learn unless it is asked to predict something. So till then, say I had initially 1000 mails. Okay. So after some time, I got some 100 mails also. I can simply add, because unless it predicts, it doesn't make any learning. So you can simply add those new instances to the data set which is already available. Okay. So that is the advantage. Like if you think about other algorithms, later we'll study. But what happens is, when you get the training data, it tries to predict and it tries to learn from the data. Now, if you add some new data, it is little different. You cannot, it is not simple to add new instances later on. So rather, when you compare your KNN, since it is not learning anything initially, you can simply add new instances. Okay. So that is one advantage. Okay. Now, there are other issues like say scaling issues. So this is not just for your KNN algorithm. Even other algorithms where we have distance-based measures, you will have this issue. Okay. So what is that issue? Attributes may have to be scaled to prevent distance measures from being dominated by one of the attributes. Say for example, say height, weight, and income are three parameters. Okay. Now height is varying from 1.5 to 1.8. Okay. And weight is varying from 90 to 300 pounds. And say income is varying from 10K to 1 million. Okay. So the values are very different, isn't it? So when you find the distance, that range is very different. Okay. So when you find the distance, actually, if in this case, if you see, income would contribute or dominate in that distance calculation, but actually it shouldn't be, because we don't know whether income is having that much importance. So what we have to do is, if there is a large varying of values in our attributes, this is, we are talking about the attributes. Okay. So if there is a large variation in a large range of values in each attribute, so what we have to do is, we'll normalize, we'll learn it later. We can understand that, we'll bring it, like we can convert all of them to like a range of 0 to 1. So they're all in same, or minus 1 to 1, something like that. Okay. So all of the attributes are having same kind of value, same range of values. So now we'll not have that issue. So whenever you have these kind of issues, like say, for example, large variation in the attribute values, and we have a distance based algorithm, then you need to scale it. Otherwise, you might get a wrong kind of prediction, learning from the model. So that is there even in nearest neighbor classification, because we find the distance. Okay. So that is one thing. Okay. Now, what about real values? Like real value in the sense, till now we were talking about classification. Like we said, we are trying to predict good or bad. Okay. What if we were using to predict the price of a particular, or temperature? Okay. Like we discussed in the initial class. KNN is used for a regression, or we can say it is like a prediction of temperature. Temperature is actually a continuous value, isn't it? So we can't tell majority is having, we find k nearest neighbors. So that is say 5 nearest neighbors, for example. And then we can't say, we may not have the same value in any of these, isn't it? It is a continuous value. So then what would be done is, we'll just find, say, if we say k equal to 5, we find the value, the temperature value of all these 5 neighbors, and then we take an average. Okay. So that's how we do it for real value predictions. Okay. So when we have real value, in the sense the output value is real, not discrete. Okay, like a regression problem. So there we do, what we do is, we find for the k nearest neighbor algorithm, we find the mean of k nearest neighbors. Okay. Now there is something called, usually our generic algorithm, like what we saw previously, our basic algorithm, what it does is, all attributes are having equal weightage. Okay. Or all instances are having equal weightage. Okay. We don't give any weightage for a particular instance or so. I was talking about instance, not attribute. Okay. So previous example, if you see, we are just taking the 3 nearest neighbors. Now there is something like, you have weighted k nearest neighbors algorithm. So what it does is, these are all different variation. Okay. The basic algorithm is what we discussed already in the previous class. These are kind of variation for different situations. Okay. So these are also there. It's not just the basic algorithm. So so what happens here? So here actually weight the contribution of each of the k neighbors according to their distance to the query. That is, we are finding say 3 nearest neighbors. Okay. Then closest neighbor would get more weightage in the prediction. Okay. So who will get more weightage? Obviously closer neighbors. So how do you find that? I mean, what kind of weight, how you will assign it? So it, you know that it is inversely proportional, isn't it? So to the distance between your query instance and that particular instance, that distance is inversely proportional. That's what we are saying. We'll give more weightage to the close or minimum distance value. So it is shown as W is approximately equal to 1 by distance, squared distance of xq and xi. Okay. So like this, for each instance, we assign some weight. Okay. And then when we predict, there is more weightage for the closest instance than the faraway instance. So in such cases, actually, I think I think that day somebody asked, if this is the algorithm, we may not have that issue of same what is it, same number of positive and negative coming up. Okay, in weighted nearest neighbor algorithm, we may not have this issue. Okay, because we are giving weightage for each of the, like say if I have 5 nearest neighbors, k equal to, in the sense the first nearest neighbor will have more weightage than the second nearest neighbor, and so on. So obviously we'll not have like equal kind of situation, like a tie kind of situation where we don't know which to take. That kind of issue will not come here. Okay, so this is maybe one approach where we can solve that issue. But anyway, I'll still go through whether we have any other approach to take if it's a normal k-means, KNN algorithm. Okay, so this is one approach where we have weighted nearest neighbor algorithm. Okay, so it is just telling that if you are averaging, then it is robust to noisy data. Then irrelevant attributes sometimes will actually dominate sometimes, because when we find we are actually using all of them, so we may eliminate some irrelevant attribute. Okay, so this slide is not very important. I just saw it, so I have just put it so that you will, when you read it somewhere, you should know about it. Okay, this is not like a very important slide. I am just putting it because in depth what is this won't be very clear, because it's not it's out of scope of particular this particular course. But we can actually, if you are interested, you can go and still find out. So like say for example, when we have like huge number of instances, okay, RKNN will not perform well, in the sense not perform in the sense it is little slow, because only when it gets something to predict, it will suddenly start finding the distance. So now say if I have 2000 males, okay, now a new mail, like there is a prediction to be made, then I'll find that new instance and all these 2000 instance, that distance between this. So it will take some time, isn't it, when you have lots of instance. So there are some variation where they calculate only partial distance. That is, say for example, they identify some attributes, okay, and then they calculate the distance based on some attributes. Like if you have some, hope you remember the difference between instance and attributes. Instance is each row or each record, and attribute is your, say, age, height, weight, etc. Okay, or say in your spam mail classification, maybe your number of messages, time of or how many recipients, etc. So so now what happens is, we can calculate based on some, say if you have 100 attributes, maybe we are taking only 30. Okay, we are finding the distance based on only these few attributes. And then if you find that the distance, this distance itself is beyond a threshold, then we will not find that particular distance itself. Okay, only if it is below some threshold we are finding, because it's already very huge, so it will not become our k nearest neighbor, something of that sort. Okay, so appropriate data structures and algorithms can be used, and we can minimize. Okay, it's, we are not calculating fully, because we know that already when we calculate with these attributes itself, the threshold, I mean, it is, the distance is above some threshold. So we stop finding the distance itself. We identify there itself that it is not the k nearest neighbor of that particular query instance. So we stop, something like that. Okay. So just understand that we don't, and there are some training tuples which are not useful, etc. Then we may remove it. So these kind of approaches to speed your algorithm. Okay. This is also available. That's all I meant. Okay, this is actually a question. What you can do is, I'll share it to you now in the end, I mean after the class. You can go through and try to figure out, the question is here. So this much data set is available. 20 instances are available. Okay, we have only 2 attributes here. Okay, ID is not an attribute, speed and agility are the attributes, and draft is the class label. Okay, now what is the question? You have speed and agility. The attribute value is given, and you're supposed to predict whether your draft is yes or no. Yes or no. Okay. Now, using k nearest neighbor, you can try with like k equal to 3, k equal to 5, etc. Okay. So maybe you can choose. I show. I think I didn't mention. You can try with k equal to 5. Okay. So you can choose, or maybe you can actually see, once you find the distance, whether it is k equal to 3, k equal to 4, etc., it doesn't make much calculations, because finding the distance is only the first task. Okay. So what you can do is, this question you can do for k equal to 3, k equal to 5, and k equal to 7. Okay. So please note that. Okay. And I'll share the PPT in the after the session. So you can just have a look and try to solve. And if you have any difficulty, let's discuss in the next class. It's clear, no? Like a homework problem you can do and come. Is that fine?
Yes, ma'am.
Yeah, just quiet distance you need to find. Okay, but k equal to 3, k equal to 5, k equal to 7. Three values you find. Okay, so that's all with this chapter. We'll just slowly begin our next chapter. I'll just introduce. Okay, next is actually naive-Bayes classifier. I'll just share my screen. Are you able to see my screen?
Yes, ma'am.
Yeah, okay. Okay. So naive-Bayes, I think you would have read or heard, or at least heard, if not worked with. I think few of you would have even worked with, if you have taken other electives and all which are related to machine learning. So naive-Bayes is like a very simple classification algorithm, more probabilistic based, not like your previous algorithm, which is a classification algorithm, your KNN algorithm, but it is distance based. Now this is more probabilistic based. Okay, so let us see what is naive-Bayes, but before that we should know what is Bayes theorem. Okay, so I have just this is all very basic things. I think you would be able to explain better than me, but if at all you have forgotten that derivation, I am just showing. So you know what is conditional probability, isn't it? So if I write P of A given B, so given that B has occurred, or given that B is already done, what is the probability of A being occurring? That's what you write it as P of A given B in the first line, isn't it? So P of A given B, we know that P of A given B equal to P of A intersection B. A and B are two events. Okay. P of A intersection B by P of B, isn't it? Similarly, if I tell P of B given A equal to P of B intersection A by P of A, that's we already know that. Now we know that P of A intersection B equal to P of B intersection A. So can we equate the right hand side of the first two equations? So that's what we have done. Okay, instead of in the sense we are not equating that. If you use the first equation, can we write what is P of A intersection B from the first equation? That will be P of A given B into P of B. So that's what I have written in the next line. Same way, in the second line, if you try to see what is P of B intersection A, that is P of B given A into P of A. Okay. So that is what is written on the line 4. P of A given B into P of B equal to P of B given A into P of A. Okay. There is nothing to solve or something. These are all very basic things what you have learned in your probability theory. Okay. Now, from this fourth line, we have just equated and got this. Now, from that, can we tell the line 5 is correct? We are just writing that we are bringing that P of B as a denominator. That's all we have done. Okay. So this is actually our Bayes theorem. P of A given B equal to P of B given A into P of A, the whole divided by P of B. Okay. So this is our Bayes theorem. Okay. That is posterior probability is equal to conditional probability of event B given A multiplied by the prior probability of A whole divided by prior probability of B. Okay, so this is our Bayes theorem. Okay, so I think Bayes theorem also you would have learned in your maths class, etc. Okay, so I don't want to jump more into what is Bayes theorem and what is conditional probability, etc. I think you are good at it. Okay, so now Bayes theorem is our base, like the from that we have derived our naive-Bayes. Okay, it is actually from this Bayes theorem is that we got our naive-Bayes classifier. Okay, so now see here we have just used like A and B, how we have used in mathematics. Now we are writing it little differently. It's the same thing. Okay, what we wrote here, P of A given B equal to P of B given A into P of A by P of B. The same thing I have written here, but in terms of instead of A and B, I have written H and D. So can we tell what is this H and D? D is our data set. Okay, and H is our hypothesis or our label, your output, etc. We can say that way. Okay. Now, so you can even tell it is y given the whole xi. Okay, so when I say p of y given the full x, you remember long back I mean the last initial class we mentioned about input vector. So given the input vector, what is the probability of particular yi? Okay, that is what we are talking about. Okay, if you want, I'll just rephrase it that way also, maybe in the next slide. I mean when I give it to you, but understand it this way, because in some machine learning books you will see it this way only. So probability of, given that the data, what is the probability of that particular hypothesis or your output variable? Okay, so for that, what are we using? Probability prior, of course, prior probability of H, the hypothesis, prior probability of D, the training data, and given the hypothesis, what is the probability of that data? Okay, so all these are used, and then we try to come on this P of H given D. Okay, so now let us so we have just rewritten it. Okay, now we want to see, this is one hypothesis. Okay, that this is the probability of a particular hypothesis. Usually which one we choose? We choose whichever is having a highest, most probable hypothesis. Okay, given the training data, we try to find the most probable. Like say we know that it may be yes or no, but we want to know which is most probable. Okay, so given that data, what is the probability that it would become yes? So which is most probable, something like that. Okay, so how do we know which is most probable? That means whichever is maximum, like you may have different values for each. Okay, and then whichever is the maximum. Okay, we'll solve problems, don't worry on that. I'm just telling how it is. Okay, so when we say argmax, we are talking about this, whichever is maximum we take that. Okay, like we told about previous thing, we were talking about that was actually the number of most number of prediction, like that. Here we are taking whichever is most probable, we take that. Okay, we will find what is the probability of yes, we will find what is the probability of no, and then we'll take whichever is highly probable. Okay, that's how we predict what is the new samples, what is that prediction, something of that sort. Okay, so whichever is maximum we are, so if you have multiple class there also, so whichever is most probable hypothesis, that is what we choose. So for that we are finding argmax of all each hypothesis we would take. Okay, like you have yes, no, etc., and given the data set. So for that, what you have to find, you are just seeing the right hand side, that is P of D given H into P of H by P of D. Okay, so we are finding the argmax of that particular term. So when we find maximum of something, each of these will have the same denominator. Like say if you have yes class, no class, etc. For all these, the data that P of D is same. So we will not repeat it always. So we are just trying to find which is maximum probability. So we'll just take the numerator. Okay, so we take the numerator what is mentioned, and that is our argmax. Okay, so that is P of D given H into P of H. Okay, so we find for each hypothesis this particular value, and whichever is maximum, that is the class or the hypothesis which we are selecting. Okay, so that is what is actually our kind of leading to our naive Bayes classifier. So now let us see. You need to tell me. So this is the question. Let me read out the question. Okay, so a patient takes a lab test. Okay, and the result comes back positive. Okay, he is doing a lab test and the result is positive. Now the test returns a correct positive result in only 98% of the cases in which the disease is actually present. Can you tell what it is? Actually, the disease is there and the result being positive is only 98%. Okay, so 0.98 by 100, so it is 0.98. Okay, so that is actually the patient has cancer and the test also became positive. That is 98%. Okay, now what is the next line telling? It is a correct negative result in only 97% of the case. That means the disease was not present and the model also gave it as negative. Okay, that is in 97% of the cases. And also there is another information given that in the whole population 0.008, okay, it's not percentage, it's the value, 0.008 of the entire population is having cancer. Okay, that information is also there. Now can you tell me what are the given parameters from this? Finding we can do next class, but you just tell me from this. There are some terms listed below. Which are the terms which we already know from this question? Somebody can unmute and say me. Where we'll fit in this 98, that is 98 by 100, which is 0.98. Where it will go? There are 6 terms written. Where we will write this 0.98? Can somebody say me?
I'm positive given cancer.
Yeah. So given cancer, there is positive. Okay. So the test returns a correct positive in 98% of the case in which disease is actually present. So we know that disease is present and the test also became positive in 98%. So given cancer and the positive. Okay. And what about 0.97? Where do we write?
Negative given.
Given cancer, given no cancer, it is negative. Okay, so minus P of minus given no cancer. Okay, that is our, what is that, 0.97. Now, what is 0.008? Probability of cancer, that is our prior probability. So P of cancer is our 0.008. Okay, so we got the value of whatever is there in the data. Now how to find, we'll see in the next class. It might take some few minutes. We are already reaching 9:20, so we'll see it in the next class. But identify, see, this is what you have to do when you get a question. Whatever you have understood properly, that you should be able to interpret properly and write it in your correct terms. Okay, then how to find it is based on the Bayes theorem that we'll see in the next class. So this much you have understood, or any doubts or anything to be discussed? Tomorrow we have lab. We'll tell in lab what we'll do, etc. We'll have a discussion and then we'll meet tomorrow afternoon. I think that's all from my side. Anything, Beena ma'am, anything to be mentioned? Okay. Students, anything you want to ask or something? Okay.